Just draw a little charge in the middle there. Do not spend an hour. If you're using a pencil and a pen and stuff, just take it easy. It's not that important. Just draw a charge out in the middle someplace. Boom. There's my charge. I want it sort of in the middle. I said in the middle of the big open space. Now, Mr. Bernard, I'm going to ask you to draw flux lines emanating from that object. Agree? At least, how many? 4. So draw as many as you want to. I'm going to draw 8 because I'm figure most of you are going to draw 4 because you're lazy. Hey, lazy is a quality that is not the worst thing.
All right, I'm fine.
You can figure out ways to do something without. If you can figure out ways to do something without work, that's a good thing. That's how many inventions are made.
So why do you tell us to do our homework?
Because you can't figure out a way to do it without the homework, and that's a bad kind of lazy.
We have the internet at our disposal, Mr. Residence.
Yes, and that'll help you with this a lot.
Don't pretend like I was sarcastic.
All right.
Damn. Hey, Randy, I did 4. You were right. I did 8 just by you.
I told you out loud what we were doing, so it's all right. Okay, now I want you to draw a closed shape around your object. By the way, if you need to draw long flux lines, I want some long flux lines. Don't draw those stubby ones. You need long ones. I want you to draw a closed shape around your electric field, around this charge. What's a closed shape, first of all? Closed shape is something that goes completely around. There's no gaps. So draw a closed shape around it. Any shape you want to. Draw yourself a diamond, a heart, a cardioid, a limassol, whatever you want to draw. Yes. Sir. Yeah, somewhere around the charge, just any shape you want. You can make an octagon. Go. Make an octagon. Any shape you want. I'm going to draw this shape here. I'm drawing an amoeba. Okay, you got it? Now, I want you to calculate the flux of your drawing. Now, Brandon, what's the flux again? The amount of what? Lines that go out of your shape. So I want you to count the number of lines that went out of your shape. Make the calculation right now. Go. You got how many? You got 8? You got 4? You got how many? 8? And how many you got over there? 8. Okay, so now I want you to draw a completely different shape. Go wild and crazy.
Like a potato.
Around, same sort of thing, right? It has to be crossing the flux line. Draw any shape you want to. I'm going to go a little even crazier than you might.
Square.
Well, you can put it inside if you want.
The cardioid is a messed up cardioid. That cardioid seems like
No, you're just drawing 2. I want to make a point.
I literally just drew a circle of a square.
Figuratively make a point, I guess. Okay, your butt's going to be bigger. Because I'm asking you the same thing again. Calculate the flux through that new shape you just drew.
4, 8, 8.
All right, how many did you get?
So if it goes through, and then also it goes in and then goes out. It can cancel out.
That gets that, right?
So it's still like.
So it's still 8 for you. Did yours change? 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 Why are they not changing?
Because it's spider.
Why is it not changing?
There's no open area. And it's all the way around.
Okay. He just said Gauss's law out loud. I hope you heard it.
I did hear it.
it has to be the same, right? Even when I do this little loop-de-loop, I've got, aha, going out, going back in, going back out. So the net flux is 1 for this one line. Doesn't matter what it is, as long as it's closed, as long as no lines can escape, the only thing that determines the number of lines is what's inside the inside. So the amount of flux is determined solely by the charge enclosed. So the amount of flux is determined solely by the charge enclosed. Now, this is a little bit of a headache because it's not measured in coulombs, is it? In fact, it matters how it permeates through the space itself. So I need some sort of a conversion to turn these lines into not just lines I picked, into lines that actually are made by a singleton charge. So I'm going to need some sort of constant. So I'm going to put a little k here for temporary record keeping. Then I'm going to figure out what that constant is. So I'm going to pick something that is so easily done that I can possibly come up with the flux for that object, coming from this direction and from this direction. So how am I going to do that? Well, what's the easiest shape to find the electric field for? A singleton line? Point charge, right? We know the electric field formula. We derived that first chapter, right? So if I go ahead and say, all right, I'm going to do a point charge here, and we're going to make it something easy. 1 coulomb? 1 coulomb. And then, could you tell me a shape for which every single place of the shape would be the same electric field from that point charge? Mr. Bernard, what shape would that be? A ring, yes. More completely, if I want to do the whole entire, I want to completely enclose it, right, three-dimensionally, I need a what? I need a sphere, right? So I'm going to draw it as a circle, a ring like he said, but I'm going to draw a sphere around this sucker. Okay? And then I'm going to say, all right, the flux is going to be the amount of lines traveling through this object are going to be equal to Q enclosed, which we said is 1, divided by, or not divided by, we haven't done divided by yet, multiplied by some constant times Q enclosed, right? Agreed? But flux is also equal to what else? EA, right? Electric field times the area it passes through. Right? So the electric field of a point charge from last chapter was what? What was it? Oh, this is a bad letter. I don't want this to be a K now all of a sudden. I want it to be another letter. What letter can we pick? Because I might you put K over here. W. I heard W. Let's go W. Let's go W. Yes.
If you unfolded a sphere, would it be a circle? Like
no.
Made a sphere.
If you have to cut it and then open up and look at an orange peel, right? You've had an orange peel before.
It's like
It's like an eight map.
Yeah.
Yeah.
Yeah. So, so the electric field is KQ over D squared, agreed? And then the area, what's the area? What is the area of the shape I wrapped around it? So it'll be a surface area, right? What would that be? Surface area is sphere. Remember the formula? You're going to by this chapter. 4 pi r squared. It's a surface area. It's an area. It's like a carpet. Area. Surface area.
Not volume. Sorry.
All right. So I'm going to keep going here. I'm going to notice Q enclosed appears on both sides of this. Agreed? All right. I'm pausing here. You guys good? Bernard, you good? We get rid of Q enclosed because that's the same charge on both sides. Agreed? Yes. Where'd it go?
Where did the cosine or the sine go?
Oh, I was going to try to slide past that without talking about it. Let's talk about it now because you asked it. I was going to see if I could get past that without anybody asking questions. It's going to, if it goes through the surface, it's going to hit it perpendicularly, right? If I draw a perfect sphere. So it's the same direction as the normal to the surface. So it's going to be 1 in that case, right? So, but I was trying to slide that under. Good job. Good catch. Good? That was good. I mean, you're thinking. So I got QQ. Oh, so my constant's over here, isn't it? I've almost got it. My constant W is going to be equal to K. Isn't this D the same as this? Well, this is the distance from the center, and this is the radius of my sphere. Those would be the same, wouldn't they? So, this is going to be an old friend of ours, K times 4 pi. Now, I'm going to go one step further and do something really, what? I'm going to do something really sick and wrong. I'm going to say I don't want that as my constant. Instead, I'm going to do 1 over it. Why? I'll explain later. Okay? So if I'm going to do that, if I want to do 1 over, so this is my thing. I'm going to do 1 over both sides. Okay? I'm going to do 1 over both sides. I'm going to go 1 over W, therefore equal 1 over 4 pi K, right? And K is that 9 times 10 to the 9th, right? And I'm going to call that 1 over W. I'm going to call it E naught, the electric permittivity of free space. So far, so good? Yes, sir.
What does W stand for?
W was the random variable we made up to go in front of my Q enclosed.
Why was the variable necessary?
Because we know the flux line is determined by the charge. We don't know it's exactly the same number of lines. We know full well that our unit should be this. We know Q doesn't give us those units. So there's something that converts the universe of charge into the number of flux lines I have. So it's that weird idea so far I've actually just drawn some flux lines. Well, at some point there has to be, if this is a real thing we're calculating, how many flux lines is it? So I'm trying to figure out what the constant would be in order to make this work. And the constant would be 4 pi K.
So that's why we're flipping it though.
We're not flipping it yet. Well, not flipping for that reason at all. What it would be is 4 pi K. So let me, because I don't want to confuse, let's go to here and say my flux formula would be this. My flux formula would be this. Flux equals 4 pi K times Q enclosed. Agreed? That would be my flux formula. Now, for reasons I don't really want to tell you about just yet, which will become obvious later on in life, it's inconvenient to use 4 pi K. It's more convenient to say if E naught is 1 over 4 pi K, then I can write this new formula in this way, and this is the way you're going to want to write it down and put a circle around it. Now, E naught is 8.85 times 10 to the negative 12. It's 4 pi K, 1 over 4 pi K. What it is. In fact, get out your formula sheet right now, because you're going to find something startling if you haven't looked at your formula sheet yet. Your formula sheet does not have K on it. It does, but it has it upside down.
I know what it looks like.
Okay, if somebody doesn't have a formula sheet, find somebody around you. You guys should like have 50 of them by now, and you're supposed to use them on every homework assignment. You bunch of hoodlums. Every time I give you one on a test, I put it in front of you.
Just like